Welcome to IT.Solution, your total network, system, firewall, and security partner.
Welcome to The Explainer. Today, we're digging right into some fascinating source material from ITN Module 9, and we're tackling one of the most brilliant behind-the-scenes mysteries in networking. Every single time you send an email, load up a web page, or stream your favorite show, your devices are actually acting like digital detectives. They're constantly working in the background to map logical identities to physical hardware. It's this foundational process called address resolution, and getting a grip on it is absolutely crucial for understanding how networks actually operate under the hood.
So picture this core detective problem. When an application on your computer wants to talk to another device, it uses a logical IP address, right? Let's say 192.168.1.7. But here's the catch, and it's a big one. Network switches and the physical cables tying everything together, they literally have no idea what a logical IP address is. They only speak the language of physical hardware identities, which we know as MAC addresses. So if your computer only knows the logical IP destination, how on earth does it actually build the Ethernet frame to deliver those bits over the physical wire?
Okay, let's dive into this. Here's our roadmap for the investigation. Number 1, 2 types of addresses. Number 2, the IPv4 ARP solution. 3, ARP vulnerabilities and attacks. 4, the IPv6 Neighbor Discovery upgrade. And wrapping up with number 5, remote network resolution.
Section 1. 2 types of addresses, logical versus physical. Let's get right into it.
To really understand this, we have to look at the dual identity every single device on an Ethernet network must hold. You can't just have one or the other, you need both. Think about it like the postal system. The IP address is highly logical. It operates at layer 3 and handles end-to-end routing. It's exactly like the postal address and zip code on a letter. It gets your data to the right city and the right neighborhood. But the MAC address, that is physical. It operates down at layer 2 and is permanently burned right into the device's network card. It handles local delivery. So in our analogy, the MAC address is the actual physical mailbox hammered into the ground in front of the house. You absolutely need the zip code to reach the neighborhood, but you need the physical mailbox to actually drop the letter off.
Section 2. The IPv4 ARP solution, the detective at work.
Okay, so we've got our zip code, but we don't know where the mailbox is. Here is the exact roadblock a host faces on an IPv4 network. Imagine a PC that knows it needs to send data to a specific IP address belonging to another machine on the network, but it's stuck. It has the logical IP, but to push those bits out of its Ethernet port, it desperately needs the target's physical MAC address. Without it, the whole communication process just grinds to a halt.
Enter our detective, the Address Resolution Protocol, or ARP. When a host hits this roadblock, it runs through a very specific routine. First, it checks its own memory, its ARP table, to see if it already knows the answer. If not, it fires off an ARP request. Now, because it doesn't know who owns the IP, it sends this request as a local broadcast. It's essentially shouting to the entire room, "Hey, who has this IP address? Tell me your MAC address." Every single device hears this shout, but only the intended target actually replies. The target sends an ARP reply directly back as a one-to-one unicast, basically saying, "Yep, that's me, here's my MAC." Finally, the sender saves that mapping into its ARP cache so it doesn't have to go shouting again 5 seconds later.
Now, you might be wondering, does it remember this mapping forever? Nope. Actually, scratch that, it really can't. Networking devices use an ARP cache timer. After a set period of inactivity, unused entries are completely scrubbed out. Why? Because networks are incredibly dynamic. People unplug laptops, hardware gets swapped, IP addresses get reassigned. If the ARP table were permanent, the network would just completely break down trying to send data to hardware that's long gone.
Section 3. ARP vulnerabilities and attacks, the impersonator. So this broadcast and reply system, it works beautifully, but it was built in an era when we pretty much trusted everyone on the network. Today, that's just not reality. There's a major vulnerability here, tied to something called a gratuitous ARP. Normally, you only get an ARP reply after an ARP request, but a host can actually just shout out an unsolicited reply, answering a question nobody even asked. And the crazy part? When a normal host receives one of these, it just blindly accepts it and updates its ARP table. So what does this all mean? Well, threat actors exploit this blind trust all the time. An attacker can fire off a spoofed gratuitous ARP, loudly claiming that their own physical MAC address belongs to, let's say, the network's main router. Every device on that local network suddenly updates their ARP tables with this massive lie. Now when hosts try to send internet traffic to the router, they're actually sending it directly to the attacker's machine. It's a textbook men-in-the-middle attack, secretly letting the attacker intercept or redirect all that critical traffic. It's a huge liability. Section 4. The IPv6 Neighbor Discovery Upgrade. Targeted questioning. Network engineers knew they couldn't keep relying on a system that was noisy and easily tricked. So with modern IPv6, ARP is entirely gone. We got a massive upgrade, Neighbor Discovery, or ND. And here is a real game changer. IPv4 ARP relies on broadcasts, shouting to the whole room and forcing every single device to process a message, even if it's irrelevant to them. IPv6 Neighbor Discovery is vastly more efficient. It uses multicast. Instead of shouting, it sends a highly targeted message to a very specific group. If a device isn't in that group, its hardware literally ignores the message, saving precious processing power across the board. Neighbor Discovery is driven by a protocol called ICMP6, and it uses 4 specialized tools to get things done. For device-to-device discovery, our direct ARP replacement, it uses Neighbor Solicitation, or NS, and Neighbor Advertisement, NA messages. For discovering the network's routers, it uses Router Solicitation, RS, and Router Advertisement, RA messages. To see this in action between 2 PCs, it's pretty elegant. When one PC needs to reach another on an IPv6 network, it sends out that Neighbor Solicitation message. But notice how polite it is compared to ARP. It effectively taps a specific group on the shoulder, saying, hey, whoever has this specific IPv6 address, please send me your MAC. It uses a special solicited node multicast address, so only the device with that exact matching ending even bothers to pay attention. The target then responds with a Neighbor advertisement, handing over the MAC address directly. Clean, fast, and targeted. And the brilliance here is the consistency. This exact same process happens when a PC needs to find the physical address of its local router. The PC sends an NS message asking for the router's MAC based on its IPv6 address, and the router replies with an NA message. The host gets exactly what it needs to build the frame and get its data off the local network. Which brings us to Section 5, Remote Network Resolution, Beyond the Local Room. Up to now, we've only talked about finding devices in the same room, right? On the same local subnet. But what if the destination IP address is halfway across the world? Well, going back to our postal analogy, your physical mailbox only handles local delivery. If a host realizes the target IP is on a remote network, it doesn't try to find the MAC address of that distant server. That would be impossible. Instead, it looks for the MAC address of its local post office, the default gateway. It uses ARP for IPv4 or Neighbor Discovery for IPv6 to find the router's physical MAC, encapsulates the packet, and confidently hands it off to the router to handle the rest of the journey. The leap from the noisy, easily spoofed IPv4 ARP to the sleek, targeted IPv6 Neighbor Discovery really highlights how much network design has matured. But it does leave us with a pretty compelling question. As networks continue to evolve away from broadcasting and towards secure, targeted communication, what other legacy foundational protocols are just sitting there, waiting to be exposed as security liabilities? Keep that in the back of your mind as you continue exploring. Thanks for joining me for this explainer, and we'll see you next time.
Thank you for watching. See you in the next episode.